Welcome back. Today we're going to talk about polar equations of conics, and I think one of the things that we need to remember right off the bat is, when we're dealing with polar, we're going to be looking at a different set of coordinates, a different coordinate system, and as we start to work on what does this actually mean, I need you to trust the process, stay with me, and we're going to pick up a lot of different pieces here, throw them into an equation, but at the end of the day, we're going to be looking at what is the structure, and how do the individual values change what's being displayed on our graph. Let's talk about eccentricity for a minute. And I want to show you a little bit of an exploration here, and we'll pick up some of those pieces right here and see kind of how this works before we get into the nuts and bolts of it. So I've got an equation here, and this is actually what the polar equation of a conic looks like. It's r equals 2 times a, and in this case, a is going to be the eccentricity of our graph. We haven't really talked about eccentricity yet, but we're going to look at what it means right here. And then it's over 1 minus a, which is eccentricity, times the cosine of theta. There are 4 different structures of this equation. You could have 1 plus eccentricity cosine, 1 minus eccentricity times sine, and 1 minus eccentricity, or 1 plus eccentricity times sine. So this could be a sine or a cosine, this could be a plus or a minus. But as we look at this, I want you to just see what happens. Right now, I've set my eccentricity to 0.6, so 3/5, and I've got an ellipse. And as we change the eccentricity, I want you to look at what is actually changing here. So I'm going to hit play. Now notice, it's headed down. My eccentricity is now negative, but I'm going to pause it. Take a look at what's happening here. I'm going to zoom out just a little bit so you can see. So my eccentricity is negative 0.8. It's less than 1. And as I step it, look at this. Now my eccentricity is negative 2.332. And look, what kind of structure do I have here? See, it's a hyperbola. And so eccentricity is going to affect the distances in a graph from the focus to a point on the graph, and from the focus to a point on the graph, and that point on the graph to my directrix. So take a look as it keeps stepping through here. Look at what's happening. As it gets more negative, look at what's going on here. My hyperbola is becoming more and more and more extreme. And as it continues to step down, watch what happens. It's going to get all the way to the point. I guess I could speed up a little bit. And now as it goes up, look at what happens. As it gets less and less negative, this distance from, let's say, if I've got my focus in here somewhere, to a point on the graph, to my directrix, is now shrinking. Check it out. And we're going to look at what these relationships look like. Look, as it gets closer. See that switch over there? Watch the changeover. 4, -3, -2, -1. Boom, right there. You see it? Look, at -1, what kind of structure do I have? It's a hyperbola, or sorry, it's a parabola, right? And so as I move my slider up, at 1, it's a parabola again. Okay, and so there's a balance here in this eccentricity that's going to show up in our graph. So check it out. Eccentricity of an ellipse. All of these are ellipses. If my eccentricity is 0, all right, my eccentricity is 0, I've got a circle. If my eccentricity is 0.3, notice I split off and I have 2 foci, but it's now kind of an ellipse. And as it gets closer and closer to 1, it's a more extreme ellipse. But then as I cross over 1, notice I've got this, these are hyperbolas, so imagine there would be an equivalent on this side, right? So this would be like the 1.11, and then it would mirror to, this would be our 1.43, and then even flatter would be our 2.0. So they've got that mirror image, and I didn't draw them effectively, but a hyperbola is more than 1. Ellipse is less than 1. A parabola is right at 1. And so here's my focus directrix eccentricity relationship. If my eccentricity is 0, or infinity, that's my directrix. And my eccentricity of 2 gives me a hyperbola, mirrored on this side. Eccentricity of 1 is a parabola, and my eccentricity of 0.5 is an ellipse. In general, my eccentricity is equal to PF over PD. And so that means that PF is equal to eccentricity times PD. Well, Mr. Sayers, I don't really understand what PF and PD are. Check it out. Let me sketch you a little graph here. My dotted line here, this is going to be my focal axis, called focal axis because it goes through the foci. And I've got some structure here. It doesn't matter because the same basic structure exists. It just depends on what happens on the other side, right? So here it looks like a parabola because it could just as easily be an ellipse going around this way. It could just as easily be a hyperbola going over this way. And inside the bowl is my focus. And I'm going to call that F. That's where this F comes from, right? That's the focus. There's a point on my graph here, P, to where this distance is PF. So think about that for a second. I've got eccentricity is a ratio of PF to PD. Well, PD, this here is my directrix. There's a 90-degree angle here. And so this distance is PD. So as that ratio changes, meaning as PF increases, right? So as PF increases, let's imagine I've got a focus in here, right? So it could be, this is an ellipse. PF would be here. Well, if my PF to my PD is 1, then these distances are the same, yeah? So that's my eccentricity of 1. Well, look at what happens here. In this case, this is longer, right? So my PF here is longer. That's the numerator, right? So this is PF, it's 2, and my distance to my directrix is 1. Well, imagine that. As you move out, look, check it out. This one's way out here, and then down this way. Well, that ratio is 2 to 1. So for hyperbola, you got to move out farther to get to the graph and then cut over to that directrix. That's going to give you a higher ratio, so the eccentricity is going to be bigger. In an ellipse, check it out. So in an ellipse, I've got this super short PF distance and a really long PD distance. That's the relationship here. And so you can draw that sketch in, but really what's happening is this ratio is changing. Let's go back to that model here. So check it out. My eccentricity is 1. Well, let me slap it on the home screen here. As I play this, look, imagine there's a focus right in here. As I get a really long distance to that graph, and then I slide over to the directrix, it's got to be, the directrix is in here, folks. Okay, so as I slide over to that directrix, short distance, long distance, hyperbola is greater than 1. But as I get into this area here, check it out. I'm going to even zoom in, right? So in this case, if my focus is here and my directrix is out here, I've got this short distance and then a long distance. Okay, so my ratio eccentricity tells me really how curvy it is, right? And then based on where it falls in a continuum, is it greater than 1? It's a hyperbola. Is it at 1? It's a parabola. Is it between 0 and 1? Or between -1 and 1? It's going to be an ellipse. So if it's E greater than 1, hyperbola. E equals 1, parabola. E less than 1, ellipse. Okay, and that's that absolute value there. Okay, so what does the polar equation of a conic look like? You're going to recognize this drawing, and it's going to go a little bit faster here in a minute with doing some problems, but we've got to understand these relationships first. Let me draw in a structure. Could be a parabola, could be a hyperbola, could be an ellipse. It's just part of that curve, right? And so what I'm going to do is I'm going to put this distance PF is equal to R. And my focus is at the pole. Right? So in polar coordinates, remember, we had, this is just a reminder, you know, as I go out, this would be r comma r cosine theta. Yeah? So our distance is our angle and then how far out. And so as I look at this, what I'm looking at is, oh, wait, so sorry, hold on. R comma theta. Sorry, so that's our angle that it opens up and then how its distance from the pole. When I look at this is my pole right here. So it's my focus, but it's also at the pole. So as I look at what these distances actually mean, stay with me. This is P. This is P out here. It's the same thing I was just talking about. P is that P point on my graph. And so my focus is F. So FP, check it out. This distance here, we're going to call it R, right? Just like in my polar coordinates. In my polar coordinates, my R is my radius. It's my distance out away from the pole. So I move this down. Right? So R is my distance out. In this case, R is that FP distance. I still need to draw in this line here. Okay? And so P here is R comma theta. Same. Just like in a focus, or just like in a polar situation. This line here is my directrix. And my directrix is at x equals k. Well, what's k? K is the distance that we need, so we're going to use k to define our equation. So the directrix is x equals k. Well, this distance here, now, because my P point is at r theta, I need to try to not squeeze it in there so you can see it. My distance PD, right, is k minus r cosine theta. Well, where does this r cosine theta come from? Remember, this right here, okay? This distance right here, this x component, is really r cosine theta. So hopefully you're with me. Focus is at the pole. PF is the distance r, just like in polar coordinates. This x component of the triangle is r cosine theta. And so my distance here, so this whole distance, right, is made up of r cosine theta, and then this k distance here. Well, so the whole thing is k. This distance here is r cosine theta. So, check it out. From the focus to the directrix is k. The distance PD is the whole thing minus just this little x component. So k minus r cosine theta. So what that means is that if PF is equal to my radius, right, r, then P and PD is equal to k minus r cosine theta. If I combine that with my equation from up here, PF is equal to E times PD, then that means that R is equal to E times K minus R cosine theta. Therefore, my equations can stem from here. So in this equation, I solved for r. So I had r equals, but I also had this r in here. And when I solve for r, I end up with an equation that looks like this. Here's the cool part. There's actually 4 equations that stem from this. So my polar equations for conics can look 4 different ways. Well, just stay with me here. My x equals d is my directrix. Okay, and so if I have a normal, regular, everyday conic section that is r equals e times d, so what we're calling d is actually, right? So d equals k. Your book notates this a little bit differently, which is fine. It's the same principle. R equals e times k, 1 plus e cosine theta. Well, check this out. That gives me my directrix is a positive x line. My conic is on the other side. And how am I going to remember this? Well, remember, the focus is on the inside, and the directrix is the distance, it's the equidistant away. And so in the second equation, you're going to be like, well, what's the difference? Check it out. If I put my directrix on the other side, it's a negative distance away. The focus has to be opposite. It's like they're magnets that repel one another. So if my directrix is here, then my focus goes this way, which means that my graph has to point that way because the focus is inside. If my directrix is on this side, my focus jumps at the pole. Focus jumps to the other side, and so my graph has to point the other way. Well, the same is true, and that's a minus equation. The same is true for if I use sine instead of cosine. So how are you going to remember that? Well, you remember that in the polar equations, cosine is my x and y, left and right, and so you can remember if it's got a cosine, then it's going to be left and right. If it's got a sine, it's going to be up and down. Well, check it out. If my directrix is positive, that means my pole has to go down. My focus is down here. Well, if the focus is on the inside, then that means, all right? Same for negative d. So if my directrix goes down, my focus goes up, and so my lines, my arms, and my graph go up. So we're going to use this with equation and logic to try to figure out, what is my equation for these conics? Here we go. Given that the focus is at the pole, write a polar equation for the specified conic and graph it. All right, maybe you don't know where to start. So here's my thing. Check out your eccentricity. Your eccentricity tells you something important. Your eccentricity tells you what kind of structure are we dealing with. Well, if you remember up here, we had a list. If it's greater than 1, it's a hyperbola. If it's equal to 1, it's a parabola. If it's less than 1, it's an ellipse. So I have an ellipse here. They're not asking you for this, but it can help you graph. So let's think for a second. If I have a coordinate plane here, and x equals 2 is my directrix, think about that for a second. Just like I just told you, if you know where your directrix is, your focus goes to the opposite side. All right, so my focus goes to the opposite side. So my focus is somewhere over here, right? Well, the focus is at the pole. Okay, so don't forget that. Your focus is at the pole, but it goes opposite of the directrix. And so what that means is my graph goes something like this. But it's an ellipse, so it's going to look something this way, right? And my graph isn't really doing it justice. Well, what does that mean? Then I'm checking out my pictures. If it opens up this way, this is the equation that I'm going to use. How did I know that? Well, I graphed my directrix, I figured out where it was, I put the focus opposite, and then saw which way my arms opened up. So, R is equal to KE. Now, Mr. Seris, I thought you said that D was K. Well, yeah. So, R is equal to K times E over 1 plus E cosine theta. Check it out. How did I know that? Well, I stole this equation. That's the equation for a graph that looks like this. So what they're telling us essentially is, hey, here's what it is based on its eccentricity. Here's what the graph looks like. Steal the equation and solve for what you need to. Well, what do I have from this? I actually have this K value here, because that means that K is equal to 2. And so what's my eccentricity? It's 3/5. So all I have to do is plug in my values. R equals 3/5 times 2 over 1 plus 3/5 cosine theta. Simplify. R equals 6/5 over 1 plus 3/5 cosine theta. Okay? To simplify, I don't want a fraction within a fraction. So what I'm going to do is I'm going to multiply by 5, because that's going to give me no fractions, right? So if I multiply the top by 5, I multiply the bottom by 5, all my fractions are going to go away. Check it out. On top, I'm going to have 6 over, and then 5 times 1 is 5, plus 3 cosine theta. This is my equation. So I sketched a graph using my eccentricity and my directrix. Using that graph, I stole the equation and filled in my values. Let's do the same thing here. Eccentricity is 1. That means it's a parabola. And with a parabola, if my directrix is at -2, check it out. Looks like this. Directrix is here. So that means my focus is over this way, so my graph opens like this. Well, what does that mean? That means I have K, so just rewrite this, KE over 1 minus E cosine theta. R equals KE times 1 minus cosine theta. Plug in my values. My eccentricity is 1. So if x is equal to -2, that means k is equal to 2. So therefore, in this one, I'm going to have 2 times 1, which is my eccentricity, over 1 minus, and this should be E, 1 minus 1 times cosine of theta. Well, when I simplify that, I get 2 over 1 minus cosine theta. Done. No need to multiply in that one because I don't have any fractions. Same thing is true for C, except my directrix is at y equals 4. And so that means k equals 4, but in this case, if my directrix is up here, then that means my focus is down this way. So I gotta steal an equation here. It opens down, so it's ke over 1 plus e sine theta. So r equals ke times 1 plus e sine theta. Plug in your values. Eccentricity is 3/2. So I've got 4, which is my k, times 3/2 over 1 plus 3/2 sine theta. Equals. This reduces, so I've got 6 over 1 plus 3/2 sine theta. I have to simplify because I don't want this. So I'm going to multiply this whole thing by 2 over 2. So I've got 12 over 2 plus 3 sine theta. That's all there is to it, guys. That's my graph there. On this one, we're going to work backwards. Okay, I'm going to do one of these because we're going to work backwards. Well, in this case, check out my equation. I know that on bottom, I want it to be 1 plus e cosine theta. And on top, it's ke. So the key piece here is this 1. I've got to get this to 1. So I'm going to divide by 2 on top and bottom, because I'm trying to get 1 in that first slot. So if I divide by 2, I have r equals 6 divided by 2 over 2 minus 3 cosine theta. Is that a plus or a minus? I covered it up. It should be a plus. And I'm going to divide that whole thing by 2. So I have 3 over 1 plus 3/2 cosine theta. And so my eccentricity is equal to 3/2, which means that 3 on top is equal to k times e. So that means 3 is equal to 3/2 times k. So that means that k must be equal to 2, right? Because if k is equal to 2, then that means that my directrix is at x equals 2, because my equation is 1 plus, look, 1 plus e cosine theta. So that means that x equals k, not x equals -k. So x equals k, so therefore x equals 2 instead of -2 because of what my equation dictates. All right, guys, thanks for watching. Stick with it. Start with that equation, find your eccentricity and your directrix, and you'll be all right. Ask me if you have any questions, and we'll see you next time.